Hi there, guys. We're about to do 1E, then 1F, 1G. We're going to do 1E here, but 1E, F, and G are all about proof. We're talking about direct proofs, proof by contradiction, and proof by induction. You can certainly expect a fair few questions in the exams to be based on proof or to prove certain statements are true. And in particular, that skill of proof by induction is a very common type of exam question when we get onto that exercise as well. Obviously, well, let's have a look at what the definition of proof is from 1E in the Oxford book. It says proof in mathematics often consists of a logical set of steps that validates the truth of a general statement beyond any doubt. Okay, so certainly it's important in our course, but of course it's really important in mathematics that we find out that something is true beyond all doubt, 100% true, and in order for us to progress to the next level and to build on these blocks of mathematics, not just simply to use maths, but to understand and develop it, we need to have this secure base and build and prove each next idea. Certainly if you do courses beyond this course, say for example mathematics in an undergraduate course at university, you'll do a lot of proof work and you'll do a lot of learning of proofs as well. Okay, so right, in this exercise here, they're talking about direct proofs. There's a couple of investigations beforehand, a bit on Pythagoras Theorem, which I'm going to talk about in a second. Let's hide this one up. And then there's a bit on square numbers here as well, the investigation 11. But I'm pretty much directly going to go to the examples, example 28 through to 33 here. Okay, so they mentioned Pythagoras. They sort of build you up in a proof there. And I'm guessing that everyone, just get rid of me, guessing that everyone knows and understands Pythagoras Theorem, or at least knows it and can apply it. A squared plus b squared is equal to c squared, and that's always true. You'd say that's identical to c squared, it's always true. And that's in your right angle triangle. I mean, it's insulting you a little bit here, but there's your A, there's your B, there's your C. For you to know that. But how many people at this stage could say, well, I can prove that this is true as well. I know that this is always true, and I can show you a proof on this. Well, I'd be kind of impressed if you could, if you knew that, because courses before generally haven't required proof. There are loads of proofs of Pythagoras Theorem, though, and here's a good visual one. So if you find yourself later on in a university lecture, or sorry, interview perhaps, and the interviewer is saying, okay, for this course at university, tell us what your favorite proof is. Maybe you'll remember this one. It's a pretty easy one to remember. So I'm just going to do this first. It's a little extra, but it kind of links to the investigation which they give you. So what we're going to do is take two squares and of arbitrary size, so any side length you want. These could be very small, they could be very large. And I'm going to just make a little mark. So I'm going to split a length into a ratio of two lengths here, and use that same ratio on each of the other lengths. And I'm going to make 4 right angle triangles. Okay. Right, so right angle triangle's got A on this length and B on this length. I'm just calling them that. And I'm going to call this length C here as well. I know that these are right angle triangles. I'm doing nothing wrong just at the moment. I'm just defining these lengths to be A, B, and C. Consistent, in fact, with what I'm trying to prove at the top. Okay, now, obviously, I could label all of these up as A, B, and C as well, and I can do that all the way around, but I'm just going to keep things neat and simple just at the moment. I can also know that this is a right angle here. I know this is a right angle because this length and sorry, this angle and this angle make 90 degrees. I know that from the triangle in the first place because this is the same as this. And take those two angles off 180 and you're left with this right angle in the corner. So I know that this and this plus 90 degrees going to give me 180, which is this half a turn here as well. So I know I've got right angles in the corner of my square as well. I know this is a square, and this this area, therefore, is c squared. Okay, right, I'm just going to sort of blank out these bits here. Now, if I rearrange those triangles again, slightly differently, like this, so I'm putting the 4 triangles like this, there's still the length of A and B, this is still the length of A and B here as well. And if I get rid of those 4 triangles, same 4 triangles, same square, get rid of those 4 triangles, and now see that I'm left with not c squared, but a squared, a times a, and b squared, so b times b there, b squared. So I can now see that c squared, the leftover area here, is the same as a squared and b squared put together, the leftover area on the right-hand side. And the leftover areas have to be the same. Okay, now because I chose any size square and I chose any size ratio on those on each of those lengths to divide each of those lengths, I've now shown that for any right-angled triangle, this is true. Okay, and so that's a geometric visual proof of Pythagoras theorem. And you can research Pythagoras theorem. There's lots of proofs of it. You can find algebraic ones as well, of course. This is shown on Wikipedia. I just found this on Wikipedia. And there's just a little animation of exactly the same thing as well. Okay, so that is a proof. That is unlikely to be a question in your exams. So let's have a look at the questions from the book then, right? So let's just take example 28. Okay, so we need to prove that the left-hand side here is equal to the right-hand side here. It's very common to label this as LHS and this as RHS here, and to work with that notation during your proof work as well. So an examiner will understand if you write LHS is equal to something or RHS is equal to something. So left-hand side, right-hand side, LHS, RHS. Okay, now we need to take this and show that it's the same as this. Now I can see that this is a sequence here, and I can see that it's an arithmetic sequence. It's going up in 2's each time. I can see that A, my first term, is 1. I can see that the common difference is 2. And if I was going to make UN in this case, I could see that I have, I can see my sequence is 2n minus 1. So it's 1 less than the 2 times table. Oh, and there is my last term. So UN there being my last term. By the way, you can call any term in the middle UR if you want to. The last term is this. So that tells me that I have n terms as well. So I've identified that I have n terms. That's kind of important. Okay, so I have n terms here, and I need to sum all of these. So now, because I've already proved the sum of an arithmetic sequence, the sum of an arithmetic sequence, or an arithmetic series, you can call that, I could just use this formula here because I've proved earlier on in 1b, I think it was, I've proved that the sum of the first n terms here is this formula here. And I could take a plus l, or there's that other formula there, 2a plus n minus 1, lots of d in the center. And if I substitute these things in here, then I should get out n squared. Now, if we put that in, we put in 2 over 2 is 1. We've got a is equal to 1. And then we've got, sorry, what am I doing 2 over 2? We've got n over 2, because I don't know what n is here. Oh, guys, I'm not going to start this again, but you can see I've got a bit of a mistake here. This is not 2. I'm being really dumb there. Okay, n is just the number of terms in this case. But the nth term is definitely this one here. So n is just n. Okay, so sorry, n over 2. And a is equal to 1. And the last term is going to be equal to n in this case. No, it's not. Gosh, I'm making lots of mistakes here. The last term is 2n minus 1. Okay. So now if I multiply that out, I'm hoping to get n squared. So again, if I simplify the bit in the center, get rid of those brackets there, it's going to be n over 2 times by 2n plus 1 minus 1. Cancel. 2 is going to cancel that. We're left with n squared. Now, I'm aware that the book does this slightly differently. So let's check out what the book does. Just copy this one here. Now the book says essentially, well, let's write this one way and let's write it the other way. Now what they're doing there is essentially a full proof. So they're saying, well, let's write it forwards in one line. Let's write the sum backwards in the other line. This, for example, would be the term before 2n minus 1. So that term there would be un minus 1, and that term there would be un. But they're writing it forwards, they're writing it backwards, they're summing each of those. They've got now, when they add these together, each of these terms is going to come to, add them together is going to come to 2n, and we'll have n amounts of 2n. Now, they've done it slightly differently because they've not relied on the formula which we've already proved. When we proved the sum of an arithmetic sequence earlier on, we did it by a method like this. So we've proved this already in 1b, so that's why I can use that. I'm building on something which we proved previously. Now they've done it really from absolute basics here, and that's fantastic. In terms of an exam question, they'd need to be quite explicit in how they frame it in order to get you to make your proof. So it's totally legitimate to rely on something else before which we've already proved. But it may be that they ask you to actually prove to start off with this formula here. So we might need to prove that one as a part of the question instead. Okay, so my proof is valid, their proof is valid. You could argue that their proof is more complete, but both are valid. Okay, well, just stitching together two videos here. So if I go on to example 29, which I just slightly messed up, I'm just going to look at this bit of information here. It says a direct proof is a way of showing the truth of a given statement by constructing a series of reasoned, connected, established facts. In a direct proof, the following steps are used: identify the given statement, use axioms, theorems, etc. to make deductions that prove the conclusion of your statement to be true. Okay, so it's just a straightforward proof. Later on, we'll find out what a proof by contradiction means and what a proof by induction means as well. But essentially, they're just saying, well, just use what you know at the moment to make, to take a series of steps forward in order to just build on what you know. So it's just a really straightforward type of proof that we're dealing with. Okay, in terms of the wording here as well, again. Okay, in terms of the wording here, an axiom, I'm just going to read out the definition for this one. If you've not come across that word before, an axiom is defined to be a statement or proposition which is regarded as being established, accepted, or self-evidently true. So this is essentially like building blocks of things which we agree in mathematics are completely true to start off with. And they use another word there as well. Let's just see what else they say. They say theorems, deductions, proof, exactly, etc. Now, in terms of theorems as well, if you want to define this one, I generally say when we're talking about Pythagoras' theorem, it's essentially just an idea. But I'm kind of interested to see what they come up with as the definition of theorem. So the theorem is a generally proposed, not self-evident, but proved by a chain of reasoning. So axiom is kind of, I would interpret that as being, an axiom is your sort of basis that you're building on, things which are obviously true, but theorems are not necessarily obvious, but we've proved that they're true by a chain of reasoning. Okay, so let's have a look at example 29 then. So example 29, so it says the sum of an odd and even positive integer is always odd. That's what we're trying to prove, and we're trying to show that that's true. They could say, by the way, show that, or they could say prove that. They mean the same thing in this question. Okay, so the sum of an odd and even positive integer is always odd. Show that that's true. Now, we can set up any integer as n belongs to our integers. Okay, n would be more common to use than x. And if we wanted another one, we could say that m also belongs to our integers. Or we could say n comma m belongs to our integers. That would include all negative numbers, it would include 0 and so on. Okay, so we've defined n and m. So therefore you could say an even integer. Oh, it says here positive. So maybe I need to restrict this to z plus, or, or likewise I could call that n plus natural numbers, which start with 1. Same thing. So if we wanted to prove that an even and an odd integer when added together is always odd, well, an even integer, even positive integer, there would be 2n. It would be doubling any integer. So if the set that we're dealing with is 1, 2, 3, 4, and so on, if that's our set of, there's our curly brackets again, that's our set for n, and 2n would be a member of the set 2, 4, 6, so on. So that would give us the even integers. Now these are even and positive ones. Now, if we want to make an odd number, we're going to need to shift this by 1. So we could make an odd integer by, if we want to start with 1, we would take away 1 from this, which say 2n minus 1. Then would give us a particular set as well. Okay, so 2n gives us even numbers, and 2n minus 1 is going to give us odd numbers. Now, take some of this back. Okay. So they're talking about any odd and even positive integer. So if I came up with, this is my even positive integer, and then I say 2n, let's say minus 1 is an odd positive integer. In fact, they're connected because this is the number before this number. They're not necessarily saying that these are two consecutive numbers. That's why we really need to say different number here. A different number is going to be dependent on a different number that we choose at the start. So we're going to need n and m. Okay, so in order to take this a little further, we're going to need to say the sum of these. So we're going to say 2n plus 2n minus 1. That's going to be the sum of these two things here. We probably need to say, by the way, as we're setting this up and explaining to the examiner, this is our even number, this is our any odd number. I'm just sort of saving a bit of space here as well. So 2n plus 2m is going to give us 2 lots of n plus m, kind of skipping a step here, and then minus 1. Now, since I think we need another line of working out, or another line of explanation here, since n plus m is going to give us another integer, then twice any integer is always going to be positive. So we're going to need a statement saying something like 2n plus m is always not only positive, but is always even because it's been times by 2. And then when we take 1 off it, it's always going to give us an odd number. Taking 1 off an even number will give us an odd number. That's self-evidently true. Okay, let's just have a look at how the book is doing this one. So they've said let m and n be odd and an even positive integer respectively. So they've already set it up slightly differently here. So they've actually said m is equal to 2p minus 1 and n is equal to 2s. So they've set it up slightly differently in this case. They've started by saying m is the odd number and n is the even number. And then they've gone further to define those based on p and s. Well, you don't necessarily need to do that. From my point of view, that's introducing more letters than are really necessary. Okay, but they've essentially done it with p and s. So they've come up with this step here, 2p minus 1 plus 2s. They've factorized, and then they've actually gone straight to the next line and said this is an odd number since p plus s belongs to our positive integers. Okay, I would probably put in an extra line of working there. I would say this is always even because it's being times by 2. Therefore, when we take away 1, we're getting an odd number. Okay. What my proof is missing a little bit here is just having a couple of definitions. I really should have said 2n is defined to be my even number, 2m minus 1 is defined to be my odd number, and therefore then I can go to this line here. Okay, right, so let's get rid of everything. For part B, it says the sum of two even numbers is always even, so that's going to be easy. It's 2n plus 2m, and then I can do m, and there we go. We've got the same logic there, saying that here is any number. This is going to be an integer, and 2 times any integer is going to be even. Okay, basically we need to factorize out a 2. Okay, and for part C, the sum of two odd numbers is always even. So we've got 2n minus 1 and 2m minus 1. If we sum those together, what we're going to get is 2 lots of n and m, but then we'll have a take away 2 here as well, and then I can factorize this. So I've got 2 lots of m plus m minus 1. So since n plus m minus 1 is any integer essentially, then timesing by 2 therefore means it's going to be even. And you're just going to need a little statement to say that. I'm not going to actually write that here. Again, you can look at what the book says. The book is perhaps a little more thorough in their explanation. And again, they're using 4 letters there. I think you can actually get away with just using the 2 letters. So my setup is slightly different. Okay, but there is a little, well, let's go back to this again. A little statement is going to be necessary at the start and at the end. So how are you setting this up? What is 2m and what is 2n, for example? And then at the end, a little statement saying, look, I know this is true here. I now know it's true because of this reasoning. So that would be useful. Now, some people, after they finish the proof, put down QED, which stands for Quod Erat Demonstrandum, and that means that which has been shown to be true, which has been demonstrated to be true. So if you want to be clever at the end, you can write QED. That just says, I understand now that I'm finished this. This is my quick way of saying, I have shown this to be true. Some people simplify that just to a little square at the end of their proof. A little square just standing for the Q, the quad. Okay, so sometimes people put a little square at the end of their writing, their working out, just to say, I have shown this to be true, and I understand that I have shown it to be true. I'm finished. Okay, let's look at example 30. Okay, so in this case, it says, show that this left-hand side is got this triple equal sign here, which means identical to the right-hand side. Now, the triple equal sign, by the way, is like if I said x plus x is equal to 2x. Well, it's more than that. This is always true for all values of x which I take. So whichever value of x I choose, if I choose 5 plus 5, that's going to be equal to 2 times 5. So it's always true for whatever value of x I take. And that's not the same as doing this. I can't say that that's always true for any value of x, because it's only true for one value of x. So this is just an equation. This is an identity. And this is the identity symbol. Okay. Now, to be honest, when it comes to exams, they're normally pretty generous with allowing you just to write equals instead. Okay, well, in this one, it would be fairly straightforward to just multiply out your brackets and simplify and end up with this thing on the right-hand side. So what we're going to say to the examiner is the left-hand side is identical to, multiply out those brackets. So we've got x squared plus 2 lots of the thing in the middle. Sorry, our middle term, if you like. 2 lots of this. I mean, we're just doing this format here, of course, right? So plus 2ab plus b squared. Oh, that's identical as well. I'm just using this format here. So the 2ab format, that's just this thing here. 2 times this. And let's take it back. And then we're missing our b squared on the end. And then b squared, therefore, is this thing squared. So we're getting a squared over 4 when we multiply that out. Oh, and we've got minus on the end there. Got this thing. So let's just multiply that out again. So we've got a squared over 4. Okay, pretty much done here, I think. This is going to cancel. This is going to cancel. And therefore, probably just write it out formally or fully. And then that is equal to the right-hand side. So there's not much that's needed in this case. It's just multiplying out and equaling the other side. Proof is done. Little square in the corner. QED. Okay, example 31. Okay, 31. Now, in this case, we've got another situation where it's just saying prove that this algebraic statement is equal to the thing on the other side. I think really they mean an identity there as well. Prove that this is equal to this thing on the other side. Well, I think it's always going to be true because this is an identical statement, a bit like we say x plus x is identical to x. It's not going to matter if what value of x n I put in here. It's going to give me the same as putting it in here as well. So I think really they mean identical to in the middle, but you can see how people play fast and loose with the identity symbol. It even happens here. Okay, so what we're going to do is we're going to take the left-hand side, and we're going to do some multiplying out. So we'll get n squared plus 8n plus 16 minus the 3n minus the 4. Let's just take that a little further. N squared plus 5n plus 12. Now I can't see that that's obviously this thing on the other side. So what I can do now is I can take the right-hand side, and let's just multiply out those brackets with n squared plus 5n plus 4. If you multiply them out and simplify it, plus the 8, now I can see that I've got the same as the thing on the left-hand side, which is equal. I might just write it out fully, in fact. N squared plus 5n plus 12, and that's equal to the left-hand side. Therefore, the right-hand side is the left-hand side. And we're done. So we've basically gone halfway with one side, halfway from the other side, and we've met in the middle. Okay, so since the left-hand side is equal to the right-hand side, we are done. That is also valid. So you can go from one side, this side to this side, you can go from this side to this side, or you can take this so far and you can take this so far and meet in the middle. As long as you end up with the same answer, it's got to be the same for both sides. Okay, example 32. I think 3 more questions to go, or maybe 2 questions. Let's have a look. Yeah, 2 more questions to go. So 32. If you're struggling at the moment, go get yourself a cup of tea. Take a little pause. Example 32. Prove that if the sum of the digits of a 4-digit number is divisible by 3, then the 4-digit number is also divisible by 3. Let's take an example. Let's take 2022. There we go. I can see 2022. You can see that the sum of those digits there is equal to 6, and since 6 is divisible by 3, then the 4-digit number is also divisible by 3. So let's just check this. I'm not doing a proof here, I'm just verifying that this is true in a particular case. I mean, I can't possibly go through all of the numbers, the 4-digit numbers which are divisible by 3 to check this. So I mean, I could do this kind of full check. I could exhaust all possibilities. It'd be pretty boring though. So let's just try this. So 3's into 20 goes 6 times, remainder 2. 3's into 22 goes 7 times, remainder 1. 3's into 12 goes 4 times. So there we go, it's divisible by 3. Now that's just an example. It's certainly not a proof. In order to set up a proof, we're going to need to do this algebraically. And I think in the book they use, they call these P, Q, R, and S as the 4 digits which are being used. So we know that this is a multiple of 3. Let's just check what they're saying again. So prove that the sum of the digits of a 4-digit number, the sum of the digits of a 4-digit number is divisible by 3. That's this statement. So we're then going to use this statement to prove that the 4-digit number is also divisible by 3. Okay. Okay, so P, Q, R, and S, I kind of like P, Q, R, and S, that's our number. But, I mean, if we write that down in algebra, that's going to be P times Q times R times S. Okay, so, okay, well, we'll deal with that in a second. But the 4-digit number is also divisible by 3. Well, the 4-digit number itself is going to be 1,000 of P, because that's in the thousands column. It's going to be 100 of Q, and it's going to be 10 of R, and then plus S. So there's the actual 4-digit number now represented in algebra. Okay, now I can see here that I've got some visitors in the background. Just finish this one off. I think I'll have to pause this one. So this is going to be our number in full. And then we're going to need to think, okay, so this is our number. And then we're going to need to think, well, how do we incorporate this? Well, I can see that if we take if we take a P off there, if we take a Q off there, and if we take an R off there, we just put them on the end, and we've got P plus R, P plus Q, R plus S. That's the same statement, that's identical. And we can now see, pretty much there, I think, that this is equal to, we've now got 999 P plus 99 Q plus 9R plus 3K. Now, I didn't fully explain the 3K at the start. It's pretty bad of me. K just belongs to the integers. Okay, so K is an integer. We definitely know that 3K then is divisible by 3 because we've times an integer by 3. So K belongs to the integers. I should have said that at the start. Okay, so I now need to show still that this is divisible by 3. I'm now going to just factorize out my 3. I've got 333p plus 33q plus 3r plus k. And there we go. Since this is now an integer, when I times it by 3, I now get an integer which is divisible by 3. So it needs to be just a little explanation of this one at the end as well. Okay, right, that's pretty much the proof. You're going to need a statement like this to start off with. That's the information which they've given. You're going to need to define your number, 4-digit number. Sorry, let's go back to that. That's in this line here. And then you're going to need to do some algebraic work using the original statement. That's what we've got here. And then using that statement, that's what we've done there. We need to sort of play around with this to force there to be numbers which we could divide by 3 and therefore take out 3 as a factor in this case. Right, we need a little statement at the end saying 3 times any integer, we know that this is definitely an integer, is a multiple of 3. Therefore, the number itself is divisible by 3 since this is n throughout. Okay, well, let's just have a look at what they've said here. They've set up slightly differently. I find this pretty difficult to read through and to have the thought of, let's just take this, to have, here we go, to have this line of thought here, I think is really tricky, but I've essentially done that in a slightly different way if you flick back through my working out. And they've also set up the number to be like this. They've said, okay, well, we've got A3, A2, A1, A0. That's the number. Those are the digits in my number, rather than writing P, Q, R, and S. Okay, so they've set that one up in A3, A2, A1, and A0. I don't necessarily think that you need that to start off with, but they've just created more rigorous algebra there. I think it's sufficient to say this, which was our line of our number itself, the 4-digit number, is P times 1,000 plus Q times 100 plus R times 10 plus S times 1. Okay. Right. Well, maybe we can finish off here. You can hear a bit of stuff going on in the background, but I think I'm fine to continue. And let's just try and finish this one off. Okay, well, this one actually I think I can do really quickly. Okay, so we can see here that we've got to try and show that the left-hand side is equal to the right-hand side. And I can see on the left-hand side here, this sum to infinity that we have is for a geometric sequence. And I can see that the common ratio is equal to -1/2. Okay, as we go from one term to the next term, we're timesing by -1/2 in each of the cases. I can easily find that out by doing, say, -64 divided by 1/32. And just put that forwards there. And I can see the first time term is A, and first time is 1/2. And I know that since R, the modulus of R is less than 1, which it is, I know that I can use a sum to infinity. So the sum to infinity formula which we have, which we proved already, by the way, we proved it in 1C, I think. Sum to infinity is equal to A over 1 minus R for a geometric progression or a geometric series. Okay, so now if we put in our half, and we've got 1 minus a half there, should get half divided by 3/2, which is half times 2/3. The half, 2 are going to cancel. We're getting a third there, and that's proved. Okay, we've now got the left-hand side, if you like, is here, and the right-hand side, well, pretty messy, is this thing at the bottom. That's equal to the right-hand side. Now, I noticed that the book does this slightly differently, and the book has split this. In fact, let's just steal this. So the book has done it by splitting it into 2 different sequences by looking at the positive numbers and the negative numbers. And then saying, well, we've actually got 2 sums to infinity, so this one and this one from positives and the negatives, and they're both convergent sequences. They're not divergent, they're convergent, as in both cases R, the modulus of R is less than 1. That's kind of strange because they've really made much more working than they really need here. They can simply, as I said, just treat it as one sequence, which is a convergent geometric sequence in the first place, because if R is minus a half, the condition for a convergent geometric series is already met. So we don't need to split this into 2, but they have done. And then they've made a completely valid proof. They've just made more work than they really need. Now, obviously, we're relying on the fact that this is true, that this is a true formula, but we proved that earlier on. And since we proved it earlier, we can now use it later. We can use it here to build on from for this particular case. Okay, guys, well, I got through there without stopping. Hopefully, you've got through it all as well. Hopefully, that's useful for you. I'm going to do 1F much later, I think. And thank you for listening in. And I'm just going to stop this one here. And yeah, I'll see you later.